Okay, so I guess I'm learning that I have to check in on my video instead of just keeping on talking. So to finish up, we have this nth term test for divergence. If I can say that the sum of a series diverges if the limit of the series as n goes to infinity either fails to exist or is different from 0. If the limit is 0, we say that the series may converge. We'll probably have to run another test. So I'm actually going to go to the bottom of the page and do an example of the nth term test. So let's write out a first few terms of this series. 1/2 plus 2/3 plus 4/5 plus 5/6. So clearly we can see this is growing. 1/2, 0.667, 0.8, and so on. So now we're going to run the nth term test. So we already should have a sense that this diverges. So let's go ahead and take the limit of n over n plus 1. So I know I get infinity over infinity, and then I can L'Hopital, I get 1 over 1. So this limit is 1. So since the limit is different from 0 by the nth term test, we can say that the sum from n equals 1 to infinity of n over n plus 1 diverges. Now we're going to take a look at the, let me move this up just a little bit so you can see what I wrote at the bottom. All I wrote was that the series diverges. Okay, so a couple more things before we move on to the next page. The harmonic series and a simple harmonic series. A harmonic series is a series in the form 1 over a to an plus b, where a and b are constants, usually integers. A series in this form always diverges. When the nth term test is applied, the limit always equals 0. So from above, it says, if the limit is 0, the series may converge. So basically what would have to happen is you'd have to run a different test, a test that we're going to learn here, other tests that we're going to learn here momentarily. Now, a special case of the harmonic series is the simple harmonic series when a equals 1 and b equals 0. We say this is divergent. We also say that this is a special case of the series from n equals 1 to infinity, 1 over n to the p power. If you recall from chapter 8, we learned about this integral. And if you take a look at the limits of integration versus the bottom number and the upper number on the series and the form, they're similar. So what we learned about this integral applies to this series as well. And to remind you, we said when p was greater than 1, we converged. When p is less than or equal to 1, we diverged. And we're going to use this again. Okay, so we're going to move on to the next page of notes. Comparing non-negative series. So this is something we're going to read about it, and then we're going to get into our direct comparison test. An effective way to show that a series of non-negative numbers converge, or in other words, all positive, is to compare them or it term by term with a known convergent series. So if you know this series converges, but you're given this one, and both series are always positive, you can compare them term by term, and that leads us to something called the direct comparison test. So I'm going to move the paper up a little bit because we're going to need some room at the bottom. Okay, so we've seen the direct comparison test before, and I mentioned this in chapter 8, I believe, that we would call this the DCT. And we say, let a sub n be a series with no negative terms, so all positive terms. We have special things that we're going to do for terms that are alternating in sign. We say that the series a sub n converges if there is a convergent series c sub n. And as long as a sub n is less than or equal to c sub n for all n, then we converge. So on the flip side, we say that a sub n diverges if there is a divergent series such that if a sub n is greater than or equal to the divergent series for all n, then we diverge. So let's go ahead and take a look at this next example. So on the previous page, when I said we were going to lean on the p-series test, I really wasn't kidding. So here's this series. I'm going to focus in a minute on the denominator, and that's how we're going to start. So I'm going to say n squared plus 1 is bigger than n squared. Now I'm going to take the reciprocal. And when we do that, then we get 1 over n squared plus 1 is less than 1 over n squared. So we do change the sign of the inequality. Now if I compare to my original function, this is still not our original function. To get there, we need to multiply both by n to the 1/2. Square root of n is always a positive number, so the sign of the inequality will not change. So I get n to the 1/2 over n squared plus 1 is less than n to the 1/2 all over n squared. Now I'm going to use my rules of exponents to do a bit simplifying. So on the left is our original, in other words, our a sub n. And over here, using our rules of exponents, this will simplify to 1 over n to the 3/2. And this is my c sub n. So now I can see that my inequality is satisfied, and I know that this series is a convergent series since p is equal to 3/2 and p is greater than 1, then by the p-series, 1 over n to the 3/2 converges, and by the dct, a sub n converges as well. So continuing on with the 4th page of notes, we're going to talk about absolute convergence. And if we know that a series converges absolutely, then the series converges. So if the series of the absolute value of a sub n converges, then the series without the absolute value converges as well. And that leads us directly to the theorem. It's called the absolute convergence. Absolute convergence implies convergence. So if the absolute value of the series converges, the series a sub n converges. So let's do an example. So let's say that I've got some series and the terms look something like this. The terms are decreasing as n grows. You might be able to guess what it looks like, and I know this converges. So now if I look at the series without the absolute values, it might look like this: 1 minus a 4th plus a 9th minus a 16th. So the terms are still decreasing. The only difference between the first one and the second one is that we have some negative signs thrown in. But either way, the impact these terms on the end have on the overall sum is going down as we add more terms. So this series will also converge. So again, if the absolute value of a series converges, then so does the series without the absolute value. So let's take a look at an example that uses absolute convergence. So we need to show that the absolute value of a sub n converges, then so will a sub n. So I'm going to start by just taking a look at the series that we have without the absolute value, without an absolute value. So the cosine of n over n cubed plus 1. N is always positive. The denominator will always be positive. So what about the numerator? Well, if we isolate the numerator, we know that the range of the numerator is going to have a range from -1 to 1 because of the nature of cosine. But the absolute value of the cosine of n will have a range only from 0 to 1. So if we do a study of the cosine of n over n cubed plus 1, and we write out a few terms, we're going to get the cosine of 1 over 2 when n is 1, plus the cosine of 2 over 9, plus the cosine of 3 over 16. Now if I think about what these cosine values are, cosine of 1 is the first quadrant. This is a positive term. Cosine of 2 is second quadrant. That's a negative term. Cosine 3 is still the second quadrant. That's also negative. I do see that the denominator is growing. This numerator has a limited range. So I know the terms are decreasing. So the terms are decreasing, some positive, some negative. So if I take the absolute value of the series, then it's the same terms, but they're all going to be positive. The terms are still going to be decreasing as we continue to add terms, but as we add terms overall, they're contributing very little to the overall sum. So again, I'm going to say terms always decreasing, and then we can conclude since the absolute value of a sub n converges, so does a sub n. And before we wrap up this video, I want to take a minute to talk about one of the most important things you're going to learn in this section. This is called the ratio test. And you can see I'm screaming at you. This is the key to success on the AP exam. This is a test for absolute convergence. This will make more sense in section 5. And we use this test to find intervals of convergence, and from there, radii of convergence. The ratio test reads as follows. Let the series a sub n be a series with only positive terms. If we take the limit of a sub n plus 1 over a sub n as n goes to infinity, and that equals a number, then one of three things are true. If L is less than 1, the series converges. If L is greater than 1, the series diverges. But if L is 1, we can't draw a conclusion from this test, then we have to run another test. So again, a repeat of what I said above. To find the radius of convergence for an arbitrary power series, we will check for absolute convergence using the ratio test. If we do not converge, there will be no radius of convergence. So this ends video 2, and we'll continue on with page 5 in video 3.